Hello everyone, welcome to The Biggest Ideas in the Universe. I'm your host, Sean Carroll, and I'm wearing what apparently is going to be the uniform for what I wear when we're doing green screen work. It turns out, experimentation has taught me that wearing red things makes it especially easy to remove the green from the background. If you watched the Q&A video that we just released, sometimes there's an extra flaw in the green screen, namely that the cats play with it, but hopefully we can avoid that this time. So the subject matter for this particular video, the last one we did, number one, was called conservation, and we basically talked about motion, but motion that was in a straight line at a constant velocity. So today we're tackling change. Now, of course, this is an overly broad word to be talking about. So what specifically do I mean when I have change in mind? Of course, if something is moving, even at a straight line at constant velocity, that's still change in a form, but it would be a very boring universe if that's all that ever happened. For an interesting universe, what you want is things bumping into each other, things being pushed around, things being forced to change how they are moving. So what we're going to go into a little bit is some of the ideas behind what we know as classical mechanics, okay, Newtonian mechanics. Remember F equals ma? This is one of the most important equations in physics. Force equals mass times acceleration. If you're moving at a constant velocity and the velocity is never changing because you're not being affected by anything, the acceleration is zero. Any deviation from that is acceleration, and it's caused in the Newtonian world by forces. However, there's a way to actually figure out what happens when you have those forces, and that way is called calculus. So really, even though I titled the video Change, most of what we're talking about, it will be calculus, the mathematical technique for studying not just change in general, but continuous change in particular. Now, why would I not just call the video calculus? You know, change is a little bit of a sexier name, right? You can run for president with the motto of seeking change. No one's going to run for president with the motto of seeking calculus. But calculus is the mathematical idea behind the accumulation of gradual, continuous change over time. So we're going to have to dig into that just a little bit. But before we actually dig into it, let's see where we were. So Newton, right, 1600s. Newton, by the way, I'm sure you've heard this a million times already. Newton did most of his brilliant scientific and mathematical work during a quarantine, during a lockdown. There was the Black Plague that was going through Europe, and Cambridge University was shut down. Newton had to go home, and he invented what we now know as classical mechanics. So I'm not quite up to that standard, but I can talk about what Newton invented during our own little lockdown here. One of the things that Newton knew about, one of the empirical pieces of information he had, was from Kepler, right? Johannes Kepler was the astronomer. I guess today we'd call him a theoretical astrophysicist, but he was the one who figured out that planets move in ellipses. He had 3 laws, in fact, Kepler. I can never remember them, so I looked them up. So one is that planets moving around the sun move in ellipses rather than in circles. So before Kepler came along, we had a conversation between Copernicus and Ptolemy. Okay, Ptolemy said that the Earth was at the center of the solar system and the sun and all the other planets moved around it. To fit the data, which Ptolemy was interested in doing, it wasn't that the sun and the other planets moved around the Earth in perfect circles. There was a big circle and there was a little epicyclic circle. There were tiny little circles around which the planets moved, and the center of the epicyclic circles would move around the big circle, and it became a terrible mess. And you might say, well, people should have just thrown that away and gone with the sun being at the center of the universe earlier. So Copernicus did that. Copernicus said, okay, the sun is at the center of the solar system, but it turns out that even that doesn't fit the data. In fact, it doesn't fit the data nearly as well as Ptolemy's system did, unless you also have epicycles in your heliocentric Copernican system. So Copernicus said, fine, we'll have epicycles. Ptolemy had them. Why not? It was Kepler who said that throw away the epicycles. We don't need epicycles, circles moving on circles to explain the motion of the planets. There's a much easier way to do it. An ellipse, you've seen pictures of ellipses. It's basically like a squashed circle. There you go. Program was able to do it. And Kepler said that the sun is at one of the focuses of the ellipse, and the planet will move around the ellipse like that. That was rule number one, first law of Kepler's laws. But then he went beyond that. This was a very important law, but then he became quantitative about it, okay? It's not just that they move in ellipses, but he says equal areas are swept out by the planet in equal times. So what does that mean? It means, if you're far away from the sun, then for every given angle that you move around, you sweep out a certain area. If you're close to the sun, you need to sweep out a much bigger angle to get the same area in your motion, okay? The area is just the area of the swept out line between the sun and the planet. So Kepler said that as the planet moves around, it's going to sweep out an equal amount of area in an equal amount of time. I have no idea how he figured this out. This is quite a subtle little quantitative law here. But what it means in practice is that when you're near the sun, you move faster, right? Because you're otherwise sweeping out less area per unit distance, so your time has to be such that you move faster, more distance in the same amount of time, whereas when you're far away from the sun, you can move more slowly. A very rigorous, precise, quantitative relation. And then finally, another quantitative relation, the period, the time it takes the planet to go all the way around the ellipse, squared, is proportional to the axis, the semi-major axis, which you can think of roughly as the radius, the distance, very roughly speaking, cubed. Okay, the period of the planet going around the sun is proportional to the semi-major axis cubed. No, we're not going to go into any details here, that's why I'm not being too specific, but these are Kepler's three laws. And it was controversial, but the idea of ellipses and these beautiful quantitative laws was certainly much more elegant and simple than all the epicycles that Copernicus or Ptolemy could have boasted of. So people like Galileo were big fans, big boosters of Kepler, and by the time Newton came along, I think the people more or less understood this was what was going on. However, what you can perceive by thinking about these rules is that they kind of work one planet at a time, right? There's no mechanism beneath this. You just state as a law, planets move in ellipses, equal areas are swept out in equal times, and so forth. You might want to know why that is true. And furthermore, if you think that the thing that is keeping the planet moving around the sun is the force of gravity, as was not necessarily clear to people like Copernicus and Kepler, who maybe thought that there were celestial spheres and there was something that was just inherent in the nature of the motion of the planets. But if you think it's gravity, then you might think, well, mostly the planet moves around the sun, but a planet like the Earth is also going to be affected by the motion of the other planets. There will also be perturbations, tiny little influences from things like Jupiter and Mars and Venus. And so maybe this idea of planets moving around in ellipses is just a good approximation. Maybe this is the spherical cow of solar system astronomy. By the way, something I wanted to mention here is that Kepler really was a theoretical astrophysicist. The data that he used to derive these laws was mostly collected by Tycho Brahe, who was a Danish astronomer who was Kepler's mentor in some sense. In some very real sense, this was the first astronomical theory of the big data era. To Kepler, working in the 1500s or the 1600s, Tycho's observations would have represented what we would now call big data, just big collections. Like Tycho didn't even have a telescope. He just looked in very, very carefully, figured out where on the sky each planet was at every different moment, and from that, Kepler was able to abstract these laws. Okay, but by the time Newton comes around, you think this is probably just the result of some more fundamental underlying mechanism. So what was that mechanism? That was the force of gravity. There's, of course, a story of Newton during this lockdown when he went home from Cambridge University, seeing an apple fall from a tree. This is a story told by Newton, by the way. Newton liked to sort of brush up his image a little bit. He tells the story of seeing the apple fall from the tree. He didn't invent gravity. People knew that apples fell from trees long before Newton came along, and they knew that it was because of gravity that apples fell from trees. What Newton's insight really was is that the force of gravity is universal, that the same force that is making the apple fall from the tree is also explaining how the planets move. So it's really universal gravity that Newton added to the game, and he added it with some equation. So Newton said that the force due to gravity, it's really a vector, but I'm going to ignore all those complications, is proportional. So there's some constant of proportionality, which we call Newton's constant, capital G for gravity. The mass of one object times the mass of the other object divided by r squared. R is just the distance between them, so this is the inverse square law of gravity. You don't need to remember any of this. None of the equations that I ever write down here are crucial parts of what we're talking about. The point is the force decreases as the distance increases. As r gets bigger and bigger, r squared is what is proportional to the total force of gravity. Who cares? Who knows what this is supposed to tell us about the motion of the planets? Well, Newton also came up with Newton's second law, F equals ma, where a is the acceleration of the object being acted on. And together, these two laws, so you have the sun, you have a planet, the sun has a gravitational force, capital M is the mass of the sun, little m is the mass of the planet, r is the distance between them. You can figure out the force acted on the planet by the sun is pulling the planet toward it, okay? This is how much force there is. What does the force do? Newton says it accelerates the particle, the object, the planet in this case. So without the acceleration, the planet would just move on a straight line at constant velocity. That's conservation of momentum. But because it's not a closed system, because it's being acted on by an external force, it accelerates the velocity changes. Acceleration is just the rate of change of the velocity. So, as last time, what I care about here is less solving some equations and getting some details, with really appreciating the philosophical underpinnings of what's going on here, the deep meaning of what we're seeing at work, okay? If you have a law that just says in vacuum everything moves at a constant velocity, that's great. If you have a law that says planets move around in ellipses, that's also great. This kind of set of laws, Newton's second law and Newton's inverse square law for gravity, are much more powerful because they don't simply work in idealized situations where there's no other force acting on it, or whether you're just a planet ignoring all the other gravitational forces. They work all the time, right? This is supposed to be absolutely everywhere, absolutely universal. And we thought this for hundreds of years. We thought this was right. It got updated in the 20th century with quantum mechanics and relativity, but this was a much more powerful paradigm for thinking about physics. So let me try to exactly mention, just re-mention what that paradigm actually is. We have some object, there's a planet, it has some velocity, okay? V is the velocity. What is a velocity? Velocity is the rate of change of the position. So you see, just from the vocabulary, that the idea of rates of change is going to become really important in this discussion. So you have a planet, it has a position, it's located at some position x. Again, I'm ignoring vector signs and all that craziness. It's just some abstract notion of position. Velocity tells you how the position is changing. Newton's second law, F equals ma, tells you how the velocity itself is changing, okay? So then you're done. If you know how the velocity is changing, you can know what the velocity does over time, and then you can figure out what the position does over time, and then you have the complete trajectory of the particle. But what is happening here conceptually is, at one moment of time, at an instantaneous moment in the history of the universe, you tell me the position of the particle, the velocity of the particle. I'm using particle in a generalized form, so planet counts as a particle here. And then you tell me what forces are acting on the particle, and you're done. I can tell you what's going to happen next, and then I can do that the next moment of time, tell you what's going to happen next, and I can work that forward all the way to the past or the future. These are reversible laws. They go in either direction of time. That was the great insight of Pierre-Simon Laplace when he invented Laplace's demon. So the paradigm here is there exists something called the state. There exists, okay, a little math notation there. There exists the state of the particle, of the object, and that includes not just the position but also the velocity, and it exists at one instant of time. And knowing the state of the particle and the laws of physics, you can figure out everything. You can figure out what happens next. From that, everything follows. Because, of course, I said you also need the forces on the particle, but guess what? The forces are determined by the states of the other objects in the universe. So if you know the states of everything, you can figure out the forces between them, and you're done. Now, actually, Newton didn't do this. Newton didn't do what we're about to explain when he wrote the Principia Mathematica. What I'm told, I never read the Principia Mathematica. Almost no one has. You know, it's not really traditional in physics to go back and read the original papers of the great people before us. I'll confess, I've never read Einstein's original papers on relativity, even though I've written a textbook on relativity. In physics, the idea is it's the ideas that matter, not their original presentation. Newton's original presentation of this stuff in the Principia, number one, it was in Latin. It took a while for it to be translated into English. And number two, he was apparently afraid of using all of the new mathematical techniques he invented. So he tried very hard to only use existing mathematical techniques so people would believe him, so people would accept it right away. Subramanian Chandrasekhar, who was a great 20th century astrophysicist, actually wrote a version of the Principia Mathematica for the common reader. If you ever want to know what Newton was actually up to in his great masterwork, the Principia, I would advise not buying either the original Latin or English, but buying Chandrasekhar's explanation of what was going on. Okay. But what Newton did do, in addition to what he wrote in the Principia, was he figured out a very general way of solving problems like this. By problems like this, I mean there's a state right now, we're telling you the rate of change of things, and from that you figure out everything. So notice what doesn't exist in this picture. I don't need to know the history of the particle. Right? I don't need to know that it was moving on an ellipse. I don't need to know what formed it or what started it. I don't need to know anything about the future, okay? There's no teleology. There's no goal toward which it is stretching. It is an instantaneous set of knowledge. Right at this moment of time is all I need to know. So if you want, you can sort of conceptualize visually this picture by imagining time going bottom to top. So you have one moment of time. This is all of space and everything in it in one moment of time. You have some particles going around in the universe, and from the laws of physics, you can figure out what those particles are going to be doing at every moment in the future, and what they were doing at every moment in the past. You don't need historical or future information. This is an incredibly powerful, subtle move in physics, just to imagine that this is the paradigm we're talking about. Okay. But to do it, to actually turn this sort of conceptual picture into results that we can then test against observations, we need some mathematical tools. And that is where calculus comes in. So calculus is the mathematical technique we have for dealing with rates of change and their accumulation over time. So what do I mean by that? Consider, a car, okay? I do not have any drawing skills, so here's my version of a car. Sorry about that. You have a car moving, okay? This is just something we're familiar with these days. It has a position, x, and x changes over time, okay? Because the car moves. You can move it forward, you can move it backward. We're just imagining a car moving down one road in a single direction, so you don't need to worry about turning left, turning right. That's when you would have to invent vectors and all that stuff, or at least x and y and z, etc. Here we just have a single variable, the position of the car changing over time. And you might think that, if you were to plot this, okay, look at this, check it out. Trying to use the capabilities of Notes Plus, which is my drawing software here. So you have time. I'm gonna make time go left to right. I'm gonna make x go up. It's a little weird, right? Because I just drew the car moving left to right for x, but just, follow along with me here because this will make the later discussion a little bit simpler. Here is the path of the car over time. And generally, it'll be a mess, right? I mean, you'll do all sorts of things. You might, stop for groceries. You might go back. You might just be on a joyride. In this weird example, you, for some reason, keep putting your car into reverse and then forward and reverse and so forth. But this is what might be the path of the car over time, okay? X as a function of t. This is what we want to be able to figure out in the Newtonian physics paradigm. We want to be able to say, okay, where is the car? How fast is it moving? What forces are acting on it? Use all that information to solve for the trajectory of the car over time, x as a function of time. Now you notice I didn't mention the velocity. In principle, the velocity is figure-outable from this information, right? In principle, at every moment of time, there exists a velocity. If you're in your car, you have a speedometer, okay? The rate at which your position is changing over time is something that is known, that is determined anyway from this exact kind of information. The question is, how do you actually do it? Well, it's hard. Like right from there, it's not at all obvious how you're supposed to figure out what the velocity is. Velocity is the rate of change of the position, but that's changing kind of wildly from that. Let's point out something that is maybe a little bit obvious, but will be helpful. If you had a situation where the car moved in a straight line at a constant velocity, if you had that situation, then it would be easy to figure out what the velocity was. So I'm not telling you what the velocity is. I'm just saying what I know is that the velocity is constant, and I know x as a function of time, okay? Well, all I have to do then is figure out what the change in x was, what the change in t was. This is x, there is t, and in this very, very simple case, where everything is moving at a constant velocity, the velocity is just the distance you traveled divided by the time it took, if you move at a constant velocity. So, let me move that to get it out of the way here for a second. So when the velocity is constant, it's just the change in distance over the change in time. This is a rewriting of the fact that the distance you travel is the velocity times the time when your velocity is constant. And therefore, if your velocity were greater on the picture, this would look like a larger deviation, right? A larger slope of the picture. So this is a slow car, and this is a fast car. Low velocity, high velocity. So in this simple world, where the velocity is constant in the simple thought experiment example, the velocity is just the slope of this graph, x versus time, the position versus time. The steeper the slope is, the faster you're moving, the more distance you travel in a certain amount of time. Oh my goodness, I completely screwed that up, didn't I? You're making fun of me there in the background. Okay. This was obviously the time, and that was obviously the distance. I'm going to leave that in, just so we know that we all make mistakes, and also I don't want to do it again. Okay, so the more distance you travel versus the shortest time, the higher your velocity is. Good. The problem is, we're not usually moving at a constant velocity. We're usually doing this kind of weird thing, right? Where you're sort of accelerating and decelerating, your velocity is changing all the time. What about then? Well, you might think that you could approximate, right? You could approximate the velocity. Like if I just did a straight line that was a good approximation to the overall curve, then I could figure out the slope of that straight line and call that my average velocity or something like that. But I don't want to do that. I want to be more specific. I want to get the actual velocity at every moment of time. So here is the idea that Newton had. For an arbitrary curve, it might be going up and down a lot. It's nothing like the straight line that we looked at, okay? But let's just take a particular point on this curve. Newton's bright idea is this. You can zoom in. That's it. That's the bright idea. Of course, there's a lot of mathematical details involved there, but look, I picked this way of explaining it because on this program, I can zoom in a little bit, okay? If you look just at this tiny little bit of the trajectory, you know, between here and here, it's almost like a straight line. You could draw a pretty straight line between these 2 points, and then you could figure out the slope of that. And then you could repeat that at every point along the curve. You could zoom in to that particular point, figure out what the approximate change in the distance and the velocity was, the distance and the time was, and then you could figure out the velocity from the slope of that. Now, it seems like it's only ever going to be an approximation doing something like that. You could approximate a curve by a straight line, and the approximation becomes better and better the more you zoom in, but it's always an approximation, right? Well, that is, in fact, the brilliance of calculus. Calculus is a way of taking this approximation and making it exact. And the idea is taking what we call the limit. The limit is, in this very, very casual way of talking, apologies to any real mathematicians out there, but this is what we're going to get in this video. The limit is a way of infinitely zooming in. It's basically a way of saying, sure, if I just take 2 points that are close by and draw a straight line between them and calculate the slope of that, I will approximate the curve. But I know the slope. But I know that as those 2 points come closer and closer, the approximation becomes better and better. So therefore, I can just say, well, what would happen if I zoomed in infinitely far? If I take the limit of a successive number of approximations, the curve looks more and more like a straight line, and I can just calculate its slope. That's what the idea of a limit does. It just zooms in infinitely. And I'm not going to go into the mathematical details here, but Newton figured them out. Leibniz, who was his competitor, also figured them out. For reasons that I do not understand, it was conventional back in those days to get brilliant scientific or mathematical results and then not tell anybody, right? Like to put them in code or something like that. Quite the opposite of our current paradigm that we have. But anyway, Newton and Leibniz both figured out a way of doing this. So basically, that's it. That's what I want to say. I'm not going to go into any of the details. Newton figured out a way to figure out the change, the rate of change of position versus time, and using a mathematical technique of infinitely zooming in, of taking the limit. That was the origin of calculus. Let me say an alternative way of saying the same thing. So I said that if the line was just a straight line, in other words, if it were constant velocity, then you can calculate the slope. Then it's very, very easy to do. Here's another way of thinking about sort of the same basic technique, the same basic philosophy. What if time were not continuous? Okay, so we had, time here, x over here, and we had this curve that was sort of waving back and forth in this smooth, continuous way. What if time were just not continuous? What if the only times that existed were a discrete set of moments at different intervals? Okay, then you wouldn't need calculus, you wouldn't need limits, you wouldn't need anything like that. All you would have to do is sort of, at any one time, if you know x, at the next time you know x, so you know x at time 1, x at time 2, x at time 3, x at time 4, you could just calculate the slope because it's a straight line. So we know how to calculate the slope of a straight line. It's just the change in x over the change in time, right? So then you could do it, but we think that time is not continuous, okay? But there is a sense in which, as this imaginary discretization of time becomes more and more finely grained, as the moments in which we allow time to exist get closer and closer together, this piecewise constant curve becomes more and more like the smooth curve that we actually think we have in the real world. So what we do here is we call this little tiny change in time delta t. Change, delta, Greek letter delta means change to physicists. And this little tiny change in x, delta x. And then what we say is, for constant velocity, we know that velocity is just the distance you travel over the time. For discrete time, the velocity can change, but at every moment, at every little interval in this discrete set of moments, the velocity is delta x over delta t, and the velocity will change discontinuously at every moment. So what Newton and Leibniz figured out a way to do is, for continuous time, they figured out a mathematical way of taking these time intervals to be literally zero, to be infinitesimal. And what they write is v equals dx dt, and they call this the derivative. And it's based on the idea of infinitesimals in, because you have to work hard at this, right? I mean, you can take the limit as the time gets, the discretization of time gets smaller and smaller and smaller. So delta t gets smaller and smaller and smaller. But as that happens, guess what? Delta x also gets smaller and smaller and smaller. So dx and dt are supposed to be, roughly speaking, and again, huge apologies to any real mathematicians out there, but roughly speaking, this is the infinitesimal change in position versus an infinitesimal change in time. So in some sense, this is 0 divided by 0, because in an infinitesimal amount of time, you don't move at all, okay? But by taking the limit, you can resolve the fact that 0 divided by 0 doesn't really exist. So I'm going to erase this just because it's sort of bad form to have it there. Basically, you can think of this infinitesimals, this idea of limits, as making sense of 0 divided by 0 in this particular case. So that's what Newton and Leibniz did. They figured out a way to take crazy curves like this. If someone gave you the explicit form, x of t equals the cosine of t or something like that, there's a set of tools. There's a mathematical toolbox for figuring out what the velocity is. For, as we say in the lingo, for taking the derivative of that curve over time. Good. There's a couple more things I need to mention before your knowledge of calculus is more or less complete, up to some mathematical niceties. I'm not going to tell you how to actually calculate any derivatives or anything like that, but that's the brilliance, that's the fun, that's the joy of doing calculus, so you totally should do it if you haven't done it already. The other thing is that you can go backwards. In other words, remember, why are we doing this? We're doing this because we are given a law of nature, F equals ma. Force is mass times acceleration. We know what the force is, okay? So we can figure out what the acceleration is. We want to use the acceleration to get the velocity, and then use the velocity to get the position. What I just taught you was how to use the position as a function of time to get the velocity. You take the derivative, but we want to go backwards. If we were given the velocity over time, could we figure out what the position was over time? I'm checking now that Caliban has not actually messed up with my green screen. Again, if the green screen is varying, that's because there's a kitty out there playing with it, but he seems to be peaceful right now. So Caliban, let us know if you want to appear in the video. Does Caliban want to appear in the video? I don't know. Hey. Yes, this is a good kitty. All right. Caliban does not know much about calculus. He doesn't really like videos, but he's a good cat. Okay. Leave our green screen alone, Caliban. So what Newton figured out is that you can, in fact, go backwards. If to go from position as a function of time to velocity is taking the derivative, going from velocity as a function of time to position is called taking the integral. And basically, we can think about the integral as being the area under a curve. So let's say that instead of being given the position as a function of time, we were given the velocity as a function of time, okay? It's a different curve now, right? It's not position versus a function of time, it's velocity now, and we have some velocity. Who knows where we got it from? Maybe it's the readout of your speedometer over time. That can happen. How do we figure out what the position was, what the analogous function of x versus t is? So what Newton and Leibniz figured out is, well, at every moment, again, this is going to be a story of limits and infinitesimals. At every moment, we know that the change in position, if we did it in discrete terms, is the velocity times the change in time. And in the limit, this becomes dx is v times dt. So what x is changing by an amount which we call v. That's what v is supposed to be. It's the rate of change of x. So when v is large, x is changing by a lot. When v is small, x is changing by a little. When v is negative, x is decreasing. Okay, that's how velocities work. So basically, we could imagine taking a little segment here, again, as if we were discretizing time, and this area under that curve tells us the amount by which the position has changed. When the curve is very tall, the position has changed by a lot, and the area under that curve is a lot. When the velocity is very low, it's only changed by a little bit. So the new problem that we have is not taking the slope of a curve, it's taking the area under the curve. But guess what? The same philosophy kind of works. If you imagine breaking up time into discrete moments, okay, then you can figure out the area under one of these little skinny rectangles is just v times delta t, if it's a discrete little bit. That's the area of this rectangle right here. When the velocity is large, that's a big area. When it's small, it's a small one. And then you add them all up, okay? So you say that x, as a function of time, is just the sum, this is the Greek sigma, the letter for sum, of all the velocities at one time times delta t. And in calculus language, this becomes the integral sign v of t dt. Again, you're not supposed to remember what all these symbols mean. It's just because you will sometimes see them in the real world. This is what they are. This big integral sign kind of is supposed to represent or resemble the letter S, just like this sigma. The Greek letter sigma is the Greek letter that corresponds to S. So S is for sum. It's the sum of all these little bits. The integral is a way of summing up all the little contributions of the change in velocity to figure out what the position is. And you can do exactly the same thing for acceleration. Newton says that F equals ma. Acceleration is the change in the velocity over time. So the velocity over time is the integral of the acceleration at any one time times a little tiny infinitesimal amount of time being passed. So if you know what the acceleration is, you can use this formula to figure out the velocity. If you know what the velocity is, you can use the formula above to figure out the position, and then you know everything. That is exactly the point. And the brilliant thing, the really wonderful thing is they are inverses of each other, integration and differentiation. So let me see if I said this. The derivative of the integral of some function f as a function of time. I write f here because it could be the velocity or the acceleration, the position, doesn't matter, equals the original function. Derivatives and integrals are inverses of each other. The area under the curve, where the curve is defined by the accumulation of something, the velocity or whatever, the slope of that area curve is the original function. That's what this says. This is the fundamental theorem of calculus. Now, despite this wonderful symmetry, derivatives are the inverses of integrals, the truth is that it's much easier in practice to do derivatives, to take the derivative of a function than to take an integral of a function. Differentiating things is more or less trivial, in fact, for almost all interesting functions, whereas integrating can obviously be can often be extremely, extremely hard. If you take a calculus class, you're going to spend a lot of time doing integrals as your homework problem. So let me close with one last philosophical point in some sense. We drew this picture of the paradigm, right? Time going up, different particles at different positions in space. All you need to know is at that one moment of time, and then you can go forward and backward. As far as we know, physics does work like this, okay? We've changed the rules of Newtonian mechanics. In the 20th century, we had quantum mechanics and we had relativity that changed Newtonian mechanics in important ways. But this idea, this sort of Laplacian paradigm, that if you tell me everything that's going on at one moment of time, I can predict the future and the past, still seems to be in place. We're not absolutely sure. In fact, the measurement problem of quantum mechanics, which we'll get to later, is an example of something where it doesn't seem to be the case that you can predict the future from the present, but that may or may not just be apparent. It may be that we just don't have enough information. We honestly don't know. But this still seems to be the basic picture. But we can imagine ways in which it might be wrong, right? Because as I said at the end of the last video, we're supposed to be open to changing our ideas about physics. That's what makes physics great, is it's never done. We're never finished. We're not finished yet anyway. So could this idea be wrong? I mean, one of the most obvious things in the world is to imagine that time and maybe space and maybe everything else actually is not continuous, right? Once Newton and his contemporaries introduced the idea of limits and the idea of calculus into the mathematical vocabulary, it became very controversial. Right? It was not at all clear that this was sensible math that was going on. And it turns out that you learn a lot of interesting things. So for example, here's our timeline, okay? And let's say this is time equals 0, time equals 1, etc., time equals 2. Here's one of the interesting things about infinity. How many numbers are there between 0 and 1? Well, there's a half, there's a third, etc. There's a lot of numbers. There's clearly a very large number. In fact, there's pretty clearly an infinite number of numbers, right? Like if you give me any two numbers, if you pick out any two locations on the number line, I can find lots of numbers in between them. That's a little tiny proof that there should be an infinite number of numbers between 0 and 1. But you can do better. In fact, the number of numbers between 0 and 1, mathematicians later showed, Georg Cantor among them, is equal to the number of numbers between minus infinity and plus infinity. So if you take the interval from 0 to 1, and you add to it the interval between 1 and 2, and the interval between 2 and 3, etc., and all the intervals to the other side, you would think you're adding more numbers. The number of numbers would go up. That is not how it works. The number of numbers between 0 and 1 is infinitely big and is the same size infinity as the number of numbers between minus infinity and plus infinity. This is a fairly mild and not very bothersome fact about infinity, but once you really get into it, there's a lot of facts about infinity that give people the heebie-jeebies, that rub people the wrong way. So there's a very strong impulse to say, well, maybe time is actually discrete in the real world. So maybe all this calculus stuff isn't even really necessary, okay? In fact, when we solve equations, when you want to put a rocket on the moon or send a probe to Mars or something like that, right? You do solve Newton's laws of motion and Newton's law of gravity, but you put them on a computer. And computers in the modern age are mostly digital computers. So what do? They discretize. They approximate the motion of the thing by looking at time as if it were actually and really cut up into discrete sets of instances, of moments of time. And that's a perfectly good approximation as long as your time interval is really, really short. So how would we ever know if time really were discrete rather than continuous? Well, there are certain arguments that say that it really is continuous, symmetry arguments and so forth, but the real answer is we don't know yet. This calculus stuff is convenient, it's helpful, it's very, very useful. You'll see it all over the place, derivatives and integrals, but we don't know if it's the way the world really works. Maybe someday we'll figure that out.